Chapter 4: Entering the Responsive Universe. One of the most important landmarks in the emergence of a new scientific view of mankind and the universe is the work of Thomas Kuhn, who published The Structure of Scientific Revolutions in 1957. This book first alerted us to the tendency of science to be selective in the way its practitioners both choose their own research and judge the work of others. Kuhn convincingly showed us that what he called paradigm thinking often led scientists to exclude areas of research, including particular findings that didn't easily fit in with the prevailing theories or constructs of the day. A paradigm is a set of beliefs about reality that seem self-evident and unchangeable. Paradigm thinking can lead individuals, in this case scientists, to defend their viewpoint against rational evidence. This is exactly what occurred in the blind allegiance to the Newtonian paradigm. Kuhn's thesis also illuminated the problem of personal investment in science, revealing the way scientists often make their careers from particular discoveries, usually at universities or private institutes, and then tend to defend these theoretical positions, seeing them as the source of their personal status, against newcomers with different ideas, even if these ideas are objectively better and more complete. Because of this problem, science often proceeds very slowly, with one generation having to retire before the next generation can have its accomplishments accepted. Kuhn's great contribution was in creating greater self-awareness and openness among a new generation of scientists. Just when the popular realization arrived that a major paradigm shift was already underway, Newton imaged the world as operating by purely physical processes of a machine-like nature, without mental or mystical influence of any kind. By following this paradigm, all the other sciences and sub-disciplines had set out to label and explain all the parts and basic processes of the world. However, at the end of the 19th century, at the very height of the mechanistic paradigm, the basic assumptions in physics that created this kind of science were being thrown into question. Suddenly, instead of being a dead, soulless place, the universe was beginning to look like a huge arena of dynamic, mysterious energy. An energy that underlay all things and interacted with itself in a manner that could only be called intelligent. The new physics. This shift toward a belief in the universe as intelligent began with the work of Albert Einstein, who in the course of several decades turned physics on its head. As Fritjof Capra has detailed in The Tao of Physics, Einstein burst on the scene when scientists were having difficulty understanding particular experimental data in the old way. The behavior of light, for instance, did not seem to fit easily into the Newtonian mechanistic view. Maxwell and Faraday had showed in 1860 that light could best be described as an oscillating electromagnetic field which distorted space as it traveled through the universe in the form of waves. The idea of distortions of space clearly wasn't possible within the Newtonian framework, because to fit with that theory, a wave needed a medium through which to mechanically travel. To solve this problem, Maxwell and Faraday hypothesized a universal ether which could serve that function. In what was later proved to be a series of brilliant insights, Einstein advanced the theory that there was no ether and that light did, in fact, travel through the universe without a medium by distorting space. Einstein further postulated that this effect explained the force of gravity as well, maintaining that gravity was not a force at all in the conventional way Newton pictured it. Instead, it was the result of the way the mass of a star or a planet also distorted space. Einstein held that the moon, for example, doesn't orbit our planet because it is attracted by the Earth's greater mass, which pulls it around as if it were a ball whirled on a string. Instead, the Earth distorts its surrounding space in a way that curves this space, so that the moon in reality goes in a straight line, following the laws of inertia, but still circles our planet in an orbit. This means that we do not live in a universe in which space expands outward in all directions into infinity. The overall universe is curved by the entirety of the matter within it in an incredibly mysterious way. This means if we were to travel in a perfectly straight line in one direction long enough over a great enough distance, we would return to the exact same place where we began. Thus, space and the universe are unending, yet finite, limited, like a capsule, which begs the question, what lies outside this universe? Other universes, other dimensional realities. Einstein went on to establish that objective time is also warped by the influence of large bodies and by speed. The larger the gravitational field in which a clock is placed and the faster the clock itself travels, the slower the flow of time relative to another clock. In a now famous thought experiment, Einstein illustrated how a clock in a spaceship traveling at speeds approaching the speed of light would operate more slowly relative to a clock on Earth. The occupants of the craft would notice no difference, but would actually age much less during their flight than their counterparts back home. Einstein also demonstrated the constancy of the speed of light, regardless of any additional motion added or subtracted to the speed. For instance, when we are traveling in a car and throw a ball forward, the speed of the ball is the speed of the car plus the velocity of the ball after being thrust forward. Not so with light. The speed of visible light, as well as all other electromagnetic phenomena, is 186,000 miles per second. Even if we happen to be going, say, 180,000 miles per second, and shine a flashlight forward, the speed of light coming out of the flashlight would not be the sum of its speed plus our own speed, but would remain constant at 186,000 miles per second. This discovery alone, once fully grasped, shatters the old idea of a mechanical universe. And perhaps his most revolutionary idea, Einstein also asserted that the mass of a physical object and the energy it contained were in fact interchangeable along the formula E equals mc squared. In essence, Einstein shown that matter was nothing more than a form of light. Einstein's work was like the opening of Pandora's box. The paradigm shifted away from the concept of a mechanistic universe, and a stream of new discoveries began to prove just how mysterious the universe is. The first new data were produced in quantum physics by such pioneers as Niels Bohr, Wolfgang Pauli, and Werner Heisenberg. Since ancient Greece, physics had ventured on a search for the basic material building blocks of nature, dividing matter into ever smaller units. That the idea of the atom was confirmed, but as physicists divided the atom into smaller particles of protons and electrons, they began to realize the surprising scale involved. As Kappa relates, if the nucleus of an atom is visualized to be the size of a grain of salt, then to accurately portray the scale of a real atom, the electrons would have to be hundreds of feet away. Just as shocking was the discovery of how these elementary particles behaved when observed. Like light itself, they seem to act both as waves and as objects with mass, depending on the type of observation the scientists chose. In fact, early in this century, many noted quantum physicists, Heisenberg among them, began to believe that the act of observation and the intention of the scientist directly affected the behavior and existence of these elementary particles. Gradually, physicists began to question whether it made any sense to even call these entities particles at all. Certainly they behaved like nothing that could, in any sense, be called material. For instance, if they were split apart, the separate units turned out to be twin particles of the same size and kind. Perhaps most astonishing of this at all is that these elementary substances have a way of communicating with themselves over time and space that is impossible according to the old mechanistic paradigm. Experiments have shown that if one particle is split in two, and one of the twins is made to change its condition or spin, then the other automatically spins as well, even if it is very far away. In response to this discovery, physicist John Bell constructed his now famous law known as Bell's theorem, which stipulates that once connected, atomic entities are always connected, a quite magical occurrence from the old Newtonian point of view. What's more, the latest superstring and hyperspace theories in physics bring additional mystery into this picture. They see a universe that includes multi-dimensions. Multi-dimensions! Although incredibly small, and reduce both matter and energy to pure string-like vibrations. As one might expect, this new description of the universe by the physicists has begun to affect the other disciplines as well, particularly biology. As part of the old paradigm, biology had reduced life to the mechanics of chemical reactions, and Darwin's mechanistic theory of evolution had allowed biology to explain the existence of the wide range of life forms on this planet, including human beings, in terms of random processes in nature, without reference to the spiritual. That life in some way evolved from smaller to larger forms on this planet is irrefutable. The fossil record is clear. But the description of the new mysterious universe by physicists has brought into question Darwin's secular formation of how evolution worked. In Darwin's conception, mutations randomly occurred in the offspring of the members of all species, giving these descendants slightly different traits. If the traits proved to be advantageous, those individuals survived at a greater rate, and ultimately the new trait became established as a general characteristic of the species. According to Darwin, for instance, a few of the ancestors of the modern-day giraffe randomly grew long necks, and because this development proved to be an advantage, reaching more plentiful sources of food, the offspring of these animals survived at a greater rate, and eventually all species of that kind had long necks. In the secular, non-mysterious universe, evolution could be conceived of in no other way. But now, various problems can be seen with these ideas. One difficulty is that recent data projections show that a completely random process would have been very slow, and it would have taken life forms much longer to reach the stage they have than the amount of time life has been evolving on Earth. Another problem is that the fossil record does not show the missing links or transitional creatures that should be there to reflect the gradual change of a species from one form to another. Certainly, multi-celled organisms followed single-celled organisms, and reptiles and mammals didn't emerge until after fish and amphibians developed. But the process seemed to jump from one fully formed species to the next, with the new species appearing at the same time in many different places in the world. The mysterious aspects of the universe described by the new physics suggest that perhaps evolution is proceeding more purposefully than Darwin had supposed. Besides biology, the new physics began to affect many other disciplines as well, especially psychology and sociology, because it so dramatically changed our conception of the outer universe in which we live. No longer can we think of ourselves as living in a simple world of solid material stuff. If we are awake, we know that everything around us is a mysterious vibrating pattern of energy, the stuff of light, and that includes us.